我很高兴的，非常高兴的，请到了这个，我可以说我的好朋友，我要用中文啊，这个洪霞教授的这个到来，他来科大访问，给一个报告。那么这个洪霞教授呢，当然我认识他很多年啊，他是1994年进入了北京大学学习，然后呢。这个98年从北京大学毕业以后去了美国耶鲁大学，所以他在耶鲁大学拿到了这个博士学位，然后从耶鲁大学博士学位结束以后呢，去了这个 Penn State， 在这个郡州在耶鲁大学的时候，他导师是 Charles M。然后呢，在这个 Penn State 的时候呢，他就是跟着他的这个 supervisor 呢是俊珠教授，所以呢就是那么结束了 postdoc 的这个研究以后，这个洪霞教授呢就去了这个 University of Nebraska-Lincoln 一个非常这个 Lincoln 就是在这个 Nebraska 州非常 beautiful 的一个小镇子，小town 都是 yes 很有这个style 的一个小town。所以呢，就是在那里物理学院Department of Physics and Astronomy 做教授，一直到现在，这个时间已经很久了这个我访问过2次就是对那里留下了极其深刻的印象，而且我聆听过洪霞教授的这个报告若干次非常多的次数了这个都留了非常深刻的印象。好，那现在我们大家欢迎
Good morning. So first, I'd like to thank Jim for the invitation. It's my great pleasure to share with you our recent studies of complex oxide thin films, membranes, and heterointerfaces, where we use strain and charge control to induce a range of interesting complex oxides. So they take the pseudo-cubic structure such as the perovskite spinel materials. Despite the structural similarity, those materials can display a wide range of electronic and magnetic properties, ranging from high-K dielectrics, ferroic behavior, and strongly correlated oxide. So this is a class of material that has a huge technological potential. For example, the high-temperature superconductors can be used for power transmission and magnetic navigation. And the multi-ferroic materials can be used to build voltage-controlled spintronics, so spintronics without the magnetic field, and that has a promise to go beyond the Moore's law limits. So what we're interested in is strongly correlated oxides, specifically multi-insulators. So if you look at this transition metal elements, they have partially filled D bands. So from a simple band point of view, those are metal. But if the electronic bandwidth is actually comparable with the strength of on-site Coulomb energy, it will open a gap. And this gap actually can be controlled by tuning the interaction, leveraging the interplay between lattice, charge, and spin. I will use a perovskite as an example. So I have this cube, and the B side cation is surrounded by oxygen octahedral. So if the cation is too small, I cannot sustain a perfect cube, and the oxygen octahedral would tilt or rotate. So this will bend the cation-oxygen cation angle from 180 degrees. And that will reduce the electronic bandwidth as well as changing the magnetic exchange. So that changes it from a metal to an insulator and changes from possibly a ferromagnetic state to an anti-ferromagnetic state. There are lots of control parameters I can use to tune the lattice distortion and the charge carrier density to induce this quantum phase transition. And for thin films, so you have more tools such as epitaxial strain, electric field effect, and the charge transfer at the interface. So we work with those structurally similar materials, combine them into heterostructures, and use this system as a model system to control charge density, lattice distortion, crystal symmetry, and dimensionality, and see what will happen. And you can see that we can produce very high quality thin films with a smooth surface morphology and high crystallinity. If you look at the TM studies, basically those are have very sharp structural interface. Lattice is well strained, and it is also chemically sharp. So I'm going to discuss two classes of oxide. The first one is the spinel nickel cobaltate. It's a promising material for spintronic applications. The second is rare earth nickelate. It's a multi-insulator, and we use ferroelectric to control its electronic state. So let's first look at the epitaxial nickel cobaltate. So this is a material have been studied for decades because it's known for its high conductivity and very rich electrochemistry. So mostly people are using it to do electrocatalysis and energy applications. The reason is it's very difficult to produce single crystals. So people are mostly working with polycrystalline nanostructures and nanocrystals. On the other hand, this material actually has a very appealing magnetic property. So first, it has very high Curie temperature. It's above room temperature. It has very high spin polarization. And it's a ferrimagnetic material, meaning it has two sublattices. One is octahedral, one is oxygen tetrahedral, and there are two sublattices spin are anti-aligned, giving you a net moment of 2 4 microton per formula unit. So very high magnetization as well. And it is lattice matched with magnesium aluminate. This is a promising candidate for magnetic tunnel junction tunnel barrier because it has it can reduce the band folding effect. So this is a promising electrode for MTJ. It also has a large magnetoelectric coupling, so we can actually use a string to tune the magnetic anisotropy. So the idea is you need to grow thin films. Make a thin film, you can make it into magnetic tunnel junctions, but actually the thin film has only been grown for 10 years, and initial studies show the quality is poor. Curie temperature and conductivity actually is compromised in thin films. So we have recently been able to achieve very high quality thin film of nickel cobaltate. You can see it has a smooth surface, high crystallinity. What's shown here is the sheet resistance as a function of temperature for films of different thickness. And you can see we can maintain metallic phase down to 3 units cell. That's 2.4 nanometer. And the sample only becomes insulating when it's reduced to unit cell when the sheet resistance reaches the quantum limit of H/E squared. So it suggests there's a dimensionality that induces this metal insulator transition. And with the metal insulator transition, you can see the magnetic order also gets suppressed. So you can see with the reducing film thickness, Curie temperature is lower. But we managed to have above room temperature, Curie temperature, even down to 3 unit cell. And the materials show very good perpendicular magnetic anisotropy when it's growing in the 001 phase. So that is a compressive strain. And if you compare the magnetic property of NCO with other magnetic nanomaterials, so here shows the plot of Curie temperature as a function of flake thickness. And NCO, its Curie temperature can actually be much higher than other correlated materials such as rusinate and manganese. And it is also highly competitive when it is compared with other magnetic 2D materials. One of the properties we're interested in is magnetic anisotropy, meaning if you have the material, which direction the magnetization prefers to stay. And it has been shown that if you have perpendicular magnetic anisotropy in MTJ, it requires lower energy for data switching. Okay, and if you put NCO on magnesium aluminate in the 001 direction, there's a very slight compressive strain, about 0.5%, but that is already strong enough to sustain the PMA down to 1.5 unit cell. So we show here the anomalous Hall resistance as a function of a magnetic field, and you can see down to 1.5 unit cell, it has a very squarish hysteresis. And if you grow in the other direction, so it's compressed actually in plane when the magnetic anisotropy becomes in plane. So it's really tunable by strain. So now what we find is not only we can have the very appealing magnetic properties, its transport property is also very interesting. What's shown here is the magnetoresistance of the film. And you notice that unlike most of magnetic oxide, it has a linear magnetoresistance. And the magnetoresistance is very, very small. It's weakly temperature dependent. This is because we have very, very nice films. And such a linear magnetoresistance can be sustained down to 300 millikelvin up to 17 Tesla. And in contrast, in the older days, people grow films with more defect states. And you can see that you have much larger magnetoresistance and has a different shape and has a high temperature dependence. So in a way, we can use magnetoresistance to gauge the quality of the sample. Then we studied the anomalous Hall effect. Previously, I showed you that this square shape reflects that the film has a perpendicular magnetic anisotropy, but the temperature dependence of the anomalous Hall effect is very strange. So it's non-monotonic, right? If you look at the high temperature, first you can see that we have this rapid increase of anomalous Hall resistance. This is because the magnetization is actually increasing rapidly. And then it reaches maximum and starts to go down, goes to almost zero at 190 Kelvin. It re-emerges again at a low temperature. But 190 Kelvin, what's so critical about it? Because if you look at the magnetization of the function temperature, nothing happened there. When it re-emerge, you can see that it actually changes the sign. So at above 190 K is basically counterclockwise hysteresis, but below it is a clockwise hysteresis. So what's going on? Such sign changing anomalous Hall effect actually can be tuned by not only temperature, but also film thickness. Here we work with a slightly thicker film. We still have this non-monotonic temperature dependence, but this time I do not have sign change. So the question is what causes this very unusual behavior? Because if you just look at magnetization, apparently 190 K, there's nothing happening for this film. It's not because I have actually changed over carrier type. I know that if I change from electron to hole, it should have a sign change, but here apparently it is in the hole state. And if you try to scale anomalous Hall conductivity with magnetization, there's no universal scaling behavior. So this means it's not like Strontium root state, there's a magnetic monopole state. Here we have something probably more trivial. In fact, if we systematically study the amplitude of anomalous Hall resistivity as a function of temperature, you can see it's quite smooth. And for all the films, they have a similar temperature dependence. So it's more likely I have anomalous Hall resistivity that increases with temperature, and it has shifted by a universal flow. And depending on the computation due to these two effects, some sample will have a sign change. So the sign change is really due to the computation of two anomalous Hall mechanisms. So now let's look at what can change anomalous Hall. So this is basically counting the barrier phase effect below the Fermi level for those magnetic oxides. And people have tried to summarize anomalous Hall observed in different materials. They find that if you scale sigma xx with sigma xy, it can be divided into 3 regions. If you have a super clean sample, then it's determined by skew scattering. So this is the extrinsic mechanism. And sigma xy should scale linearly with the sigma xx. If it's a band intrinsic barrier phase effect, then it's sigma xy is independent of scattering mechanism. So you get the constant. If it's in dirty region, then your barrier phase, your anomalous Hall conductivity is really due to scattering, and it has a power law scaling with power exponent 1.6. And most of sample would follow this kind of scaling behavior. And if we look at the sigma xx for our NCO sample, it's right at the boundary between the moderate dirty and the dirty regions. So we our hypothesis is you can actually add up these two contributions and see if it can fit, right? So indeed, that's what we do. We try to scale sigma xy as a function of sigma xx for our samples. And for the high temperature region, for all the thickness, we can use this very simple scaling behavior, two contribution. One is a constant due to Barrier phase effect. The other one is due to the impurity scaling behavior with exponent 1.6, and it fits very well. Only at a low temperature, we have a constant. So this is either due to band intrinsic effect or side jump. If you push it to even thinner films, you can see that gradually, when the sample conductivity becomes lower and lower, close to the metal-in-situ transition, this band intrinsic effect actually disappear. And for both high and low temperature, you can use this simple scaling behavior to describe it. And we try to actually compare the anomalous Hall resistivity with metallicity of the sample. Indeed, we can well describe different phases, what kind of anomalous Hall you would expect. In the dirty metallic region, it's actually dominated by dirty metal plus intrinsic effect. In the weak localizer region, you have a constant due to either side jump or band intrinsic behavior. When it's strongly localized, it's dominated by dirty metal behavior. And you can see that for NCO, actually film thickness becomes a very, very important control parameter because it changes the metal-in-situ transition, change the Curie temperature and magnetization, can tune the coercive field, and can tune the sign and the magnitude of anomalous Hall effect. So basically, you can use the film thickness to tailor the magnetic behavior of NCO for different applications, either for sensors or for MTJ. Okay, and another thing we observe is we see something that on top of anomalous Hall, you can see something that is actually normally associated with a chiral spin texture. So we know that most of the well-studied skyrmion, right? You have a background with spin in one direction, and at the core, you have the other direction, and spin try to rotate either in the neo type or block type. And the key to have a non-collinear spin alignment when you change the spin direction is what's known as the Orszynski-Maria interaction. So this one requires you either break the inversion symmetry and have high spin optical coupling. Okay, so we actually see a signature in magnetotransport measurement that we may have this kind of chiral spin texture in NCO. Here I compare two films of the same thickness. One is 001. This is what I just showed you, and this one is the 110 direction. So first thing you notice is there's no hysteresis. This is because the magnetic anisotropy is actually in plane. So you have no hysteresis. You are just flipping the spin direction. And if you just trace the envelope of the amplitude, it's again a non-monotonic. So you have this rise, it goes to 0 around 100K, and then it rises again, switches sign. But what is interesting is on top of a normal Hall effect, which basically is a linear one, anomalous Hall effect, you also have this kind of small wiggles that is associated with the topological Hall effect. So this is probably most pronounced at the 100K because this is where it's about to change sign, so anomalous Hall effect becomes 0. And you can see this. And we have basically the anomalous Hall, topological Hall amplitude extracted, and find it has peaked around I think 10K, and that is far from Curie temperature, so we can rule out spin fluctuation as the origin for this topological Hall effect. And it's a possible sign that we indeed have a topological spin texture. The question is, what is the origin of this topological spin texture? First thing we can rule out is skyrmion, because skyrmion actually requires perpendicular magnetic anisotropy. You need to have a spin outer plane. But we know for this one, the spin is in plane. So what is likely to happen is you have miron. And the miron comes in pairs, so you have bimeron of this kind of structure. So to have a better idea that do we actually have the magnetic spin textures, we did the magnetic force microscopy studies. So this is the anomalous Hall effect. Let's just compare it with the MFM imaging. If we are in the single phase region, okay, you see only anomalous Hall effect, and basically you have a uniform single domain structure. And when you are actually at the region where you see topological Hall effect, you are going to see magnetic bubbles, okay? And go to high field, again, you have this single field region, and your anomalous Hall effect actually appears only when the magnetization is about to saturate. So it does support that we have some topological spin texture that appear. Another thing we notice is if you look at it, it has a kind of a characteristic length that is 300 nanometer, and it always goes from a valley to a peak structure. So this is a theoretical modeling of bimeron in ferromagnetics. And you can see that if we compare the experimental data with simulated data, they have similar length scale, about 300 nanometer, and then they have this kind of from valley to peak structure. So this gives us confidence that indeed we have observed bimeron structure in this system. So this is how we actually tuning the magnetic anisotropy to host the chiral spin texture. Another thing we have done is for totally different reason. So we're recently interested in fabric oxide membrane. The reason is very easy to understand, because van der Waals material has been very popular because you can exfoliate, you can build structures by stacking. Oxide, people think it cannot because it requires epitaxial growth. But if you can actually suspend the oxide, I can also build non-lattice matched multifunctional heterostructures. So we try to suspend nickel cobaltate by growing it on a water-soluble material, strontium aluminate, and soak it into water, and then scoop the suspended flakes out. You can see that this is a nickel cobaltate epitaxial grow on strontium aluminate buffered substrate. It's very smooth. After water etching, it becomes rougher, but it is still single crystalline. So this is the X-ray data. And in water, you can basically pick up this flake and do lithography, and basically following exactly the procedure you would do with the van der Waals material. And this is first we study the temperature dependence. We find that the sample is no longer metallic. It's actually more insulating compared to their epitaxial counterpart. But this is before water etching, this is after water etching, and resistivity does not change a lot. So this says like probably this is because the growth introduced more defect. And I mentioned that you can use magnetoresistance gauge to check the crystallinity of the film. So we compare the magnetoresistance of different systems. And what is interesting is this is epitaxial grown on strontium titanate. So it's not a lattice mesh that well. And this blue one is the NCO membrane. So NCO membrane, even though it's more insulating, its magnetoresistance is more linear-like. And it has smaller magnetoresistance. So it tells us that there are different mechanisms actually contributing to resistivity and magnetoresistance. So now what we did is study the anomalous Hall effect in it. So this is before water etching. NCO is epitaxially bonded on the substrate. If you do anomalous Hall effect, again, you would see this non-atomic monotonic temperature dependence. There's a sign change. The hysteresis is no longer very squarish, meaning you probably have candid spin. The magnetic z-axis is not perpendicular nor in plane. Now we water etch it. At high temperature, everything looks very similar. We have similar Curie temperature, similar sign change temperature, similar amplitude of the anomalous resistance. But surprisingly, you actually see topological Hall effect at a low temperature. The origin of this topological Hall effect is not clear at this point. Requires MFM study on this sample, which is currently going on. So this is a first material system I'd like to discuss. It's related to the magnetic properties. The second one is more like related to electronic properties. So it's a rare earth nuclide. So the initial incentive is have a funding that is supported by semiconductor research cooperated to build next generation electronics, because we know silicon cannot sustain Moore's law. Do you have alternative? We have an alternative, which is a device concept proposed several decades ago. It's a Mott transistor. So you work with a Mott insulator that you can tune it from insulating state and metallic state using Curie density. So what if we use a field effect to induce this insulator to metallic change? The advantage is the Mott insulator has intrinsically very high Curie density in the on state. So that means its screening length is smaller than 1 nanometer. So you can make a channel smaller without a short channel effect. You can turn channel off. And we want to use actually a ferroelectric-gated. So you have normal polarization to deplete or attract carriers. And so this is voltage controlled, means it has low power. So it is proposed many years ago, but almost three decades ago with not much success, because the key advantage actually is also the key curves. If you have very high Curie density, that means I do not have a solid state gate that produces enough displacement field to tune the Curie density. That means the on-off ratio will be very small. And in the insulating state, basically ferroelectric is known like has a depolarization effect. If you do not have enough switching charge, you do the spontaneous switch back. So the sample is not stable. So basically, what we want to do is address these two challenges to realize the full potential of Mott transistors. And what we worked with is use a ferroelectric gate that's lead zirconate titanate, known to have very high Curie temperature and high polarization field. And for the correlated channel, we work with the rare earth nuclide. Rare earth nuclide is known to have strong coupling between the magnetic state, the electronic state, and lattice distortion. So here is a phase diagram versus the tolerance factor. So 1 means you have a perfect cubic. The smaller number, the more distorted it is. So we have one element, lanthanum. Lanthanum nuclide is metallic because it has a very high tolerance factor. With reducing tolerance factor, the sample changes to insulating state and the TMI increases. And for some of them, the metal insulator transition and the magnetic transition actually is coupled, but then it starts to deviate. So we studied basically 4 different nucleids with different TMI. I want to see what effect they can produce. So if you look at here, the first thing is all those samples has a finite size effect, meaning if you reduce the film thickness, there's a metal insulator transition for strontium ceramium nuclide. It actually is insulating for all different thicknesses. But for the other one, you have metallic phase at room temperature. When film is thick, when it's very thin, it becomes totally insulating. So why we care? Because let's consider what happened for the field effect. The field effect is we have a parallel plate capacitor, right? And basically, the gate produces a displacement field that changes the Curie density at the interface to screen that displacement field, so it becomes continuous. So the first thing we have to consider is the Curie density. Okay, so if the displacement field or polarization of a ferroelectric is only on the order of 10 to 15 per centimeter squared, and intrinsic Curie density in the materials 10 to 16, I can only produce 10% of change. So that's not a lot. The second important parameter is the data layer, because apparently the 2D carrier density is always lower if I can work with a thinner film. But we discussed if I reduce the film thickness, the film becomes totally insulating. Insulating film does not have free carriers. There's strong depolarization. I cannot really switch the polarization anymore. So we prefer to work with a material that has the smallest data layer thickness. So the more metallic material it is, it has smaller film thickness. So let's compare our approach with what has been done in literature. So basically, people are trying to tackling the problem using two approaches. One is working with intrinsically lower carrier density. So, but we just want to work with high carrier density material to reduce the shorter channel effect. So this defeats the purpose. Another thing is really to reduce the film thickness. Okay, so this approach has been intensively invested by my PhD advisor, Charles San's group, and with not much success. The highest on-off ratio they have achieved is around 11.4. We observe similar effect. So we have basically ferroelectric-gated rare earth nuclide channels, and we systematically tune the thickness. And you can see that indeed, in the metallic phase, they follow more or less the same scaling behavior. And the lower you can reduce the channel without touching the data layer thickness, the higher ratio you can achieve, and the highest one is on par of what have been reported previously. So it seems like an intrinsic limit that you cannot really overcome. So we thought an alternative approach. So the problem is if I just reduce the film thickness, the sample becomes dead. If I make the film has lower carrier density, then it doesn't give me the good scaling. So what if I can have a channel that the carrier density is not uniform? I only sustain the high carrier density at the interface with the ferroelectric gate, but dump the rest carrier density from the rest of the channel, so that I can actually still sustain a sufficient overall charge density to screen the polarization, but only the central part has high carrier density to be modulated by the ferroelectrics. So we thought what we can do is actually interface with the rare earth nuclide with something that has intrinsically 10 times lower carrier density than some strong-10 nuclide, manganite. And we have done XPS and XAS to study the bilayer systems to verify that indeed we have created such a tapered carrier density profile. So you can see that there's about 0.1 electron per manganese transfer from LSMO to nucleus, which means a whole transfer from nucleus to LSMO. And you can see that if you compare different combinations of nucleus with LSMO, this is more or less the same magnitude effect. And this is huge because if you calculate what a 2D density corresponds to, it's actually comparable with the polarization of PZT. So I have a top gate PZT and bottom modulation comparable with that. So I doubled my modulation capacity. And let me just show the effect. In fact, it's quite striking. So here I have two channels with exactly the same thickness. This is a single layer channel, 9 unit cell of strong-10 neodymium nucleate. This is a 4 unit cell of SNO, adding 5 unit cell buffer layer. The same thickness, and you can see that the resist switching ratio changed from 5% to 300%. If we compare lanthanum nucleate, again, 5 units lanthanum nucleate give you 32%, and if you use 3 units of LNO, inserting 2 unit cell buffer layers become 30,000%. So that is 1,000-fold enhanced resistance switching. So again, we want to learn what is a scaling behavior. So this is a scaling behavior for single layer SNO, and this is a scaling behavior for the bilayer channel. There are a couple of things I want to point out. The first thing is for the same channel thickness, we have more than 2 orders of magnitude enhanced resistance switching ratio. The highest ratio for SNO is bilayer is 7.4. What is interesting is if I have a 3-unit cell SNO, inserted an additional buffer layer, you would think that I've been working a thicker channel, the effect should be smaller, but actually its effect is actually larger. So what that tells you is I cannot treat SNO and LSMO 2 channel as a parallel, independent with each other, with parallel conduction, right? There must be some synergy as an interface. And this kind of enhancement has been observed of all thicknesses. So if you have SNO 2.5, you insert the additional channel, the effect becomes smaller. So that kind of testify our hypothesis that indeed we have interface charge transfer, and we could try to probe what LSMO layer would give you the largest boost. And it's about 2 nanometer that is comparable with the calculated charge transfer length. So also support that our scenario is actually valid. So now we compare what we observed this in all the nucleate combinations. So this is neodymium nucleate, and you can see that it gives a larger effect because neodymium nucleate has a smaller dead layer thickness. And next is LNO. This one actually gives a record high of ratio of 385. I mentioned like after 2 decades, people have achieved 11, and now we have a much better effect that is non-volatile. And the key is really first, we have effectively reduce the active field effect carrier density so that it can enhance the resistance switching. But what's more is we have this extended buffer layer that can still provide polarization screening. So it also improves the retention. So that brings me to the end of the talk. This is work done by generations of postdoc and graduate students, especially led by Xuegang Chen. He's actually now in Anhui University, and Le Zhang, Kun Wang, and Yifei Hao, Qiu Chengwu. We have collaborators help us with DFT calculations and low temperature measurement and TM studies. Actually, Wei, thank you for your contribution before you left the BNL. Okay, I'm very disappointed I didn't see many students, but anyway, so if you can encourage your students to apply to PhD in UNL, specifically working for me, that would be nice. So I mostly discuss my research in complex oxide. We actually have 3 research areas in the lab. One is scanning probe microscopy. We do PFM, MFM. I showed a little bit of MFM studies. We also have a large chunk is basically combining ferroelectric with 2D material, one-to-one materials. This is active research, so I want to recruit talented, motivated students. So please spread the word out. Thank you. And yeah, that is basically the end of the talk. Thank you for your time. I'm open for questions. Thank you.
It will be better if it's online, right? For the ad. Right.
Well, it's better. It's coming from the words of their advisor, right?
Yeah. Okay. Anyway,
中文吧。
好吧，那个我们非常感谢这个洪霞教授的这个报告哈。这个大家有什么问题吗？这个 有没有什么问题？我们可以，对，好，很好。
孟霞老师你好，非常精彩的报告。我很感兴趣这个 NCO 这个体系。我的感觉这个体系非常像另外一个这个很知名的氧化物，就是 ferrimagnetic。特别是它的这个霍尔的 sign change。
对，就是它还是有点不一样，因为那个是张守成是说它是一个 magnetic monopole 嘛。
对，我想问的就是这个，就是你的感觉，因为对于 SRO 它是一个 40 oxides，它里面有比较强的 spinel 的 coupling， 所以这件事情似乎是不太奇怪的，比较就是 topological non-trivial band， 就是不太奇怪。那么在 NCO 这个体系里面，这个 sign change 它是一个什么样的机制诱导的？
我们认为它是 extrinsic， 就不是，因为我们就是他们其实一个 evidence， 他们有一个 universal scaling， 他们做那个 sigma xy versus magnetization， 他们所有的都可以 fall 在同一个 curve 上，我们是完全没有的。所以我们其实觉得是有两个 mechanism， 一个就是你 intrinsic barrier phase， 然后一个就是那个 dirty metal scattering， 然后这两个它刚好呢就是给了你不同的 sign。然后呢，那个 binding intrinsic effect 是 temperature independent， 是一个 constant。然后那个 dirty metal， 你看我是实际上我的 scattering 是在变化的嘛，因为 material becomes conductive at low temperature， 所以我的那个 contribution 呢是 temperature dependent， 所以这两个加起来给了我们这个 sign change， 所以它是一个 competing 的 effect。这就是为什么我们 tune thickness 如果 film 特别厚的话，它就是更加 crystallinity 更加高的情况下，其实是没有 sign change 的。
再追问一个，就是关于这个拓扑霍尔 topological 霍尔，就是它也是，就在 SRO 体系里面，这件事情其实有很长时间的争论，关于这个 hump 到底是真的由这个 Skarmian 或者是其他的拓扑自旋引起的 topological effect，还是一个非均匀性导致，比如说两个不同方向的。
对。我最近还审了一个说是非均匀就是两个叠加。
所以我想就在这个体系里面，你看它的这个 topological effect 似乎也是在出现 sign change 的附近，看到了这个效应。所以你们有没有比如说对这方面有一些考虑？
对，我们最开始是有考虑的，就是尤其是我最近还审了一篇文章，说是做的非常好，就是两个叠加的。这就是为什么我们要做 MFM。因为 topological effect 这个东西太玄幻了，就是说它其实是可能有各种原因的。然后我们是看到了非常重要的一点，就是我们是看到那个 magnetic bubble domain 是只有在有 topological 的地方，就是我刚刚秀的是在就非常 narrow， 大概就是几个 K， 就是3.4到3.6。
在那个范围，你可以把 density 跟那个值就是关联起来吗？
我们还没有做到那一步。但是现在就是说，而且我们就是看了这个 length scale， 就是这种 pair 的，它就基本上都是这种 pair 嘛，它就是300 nanometer， 跟人家 simulated 其实就是 bimeron 的 structure 也是一样的。就是我觉得你必须要有这种另外一个方法来 support 的。然后我们也做了 magnetization measurement 的，然后我们看到实际上是一个 phase， 不是有两个那个 magnetization， 因为要不然的话，他们其实是可以看到 magnetization 它有两个stage， 所以这些我们都做了 check。然后 NCO 其实是蛮有意思的一个系统，因为它有一个就是它有一个在 dirty 只有在 dirty 的情况下，它有几个 magnetic 的transition， 就是你如果是特别 beautiful 的 system 呢，它是一个特别 sharp 的 PMA。但是如果稍微 dirty 一下，他们说它其实有一个 spin canting phase， 还有一个 toroidal。就是一个旋转性的 magnetization 轴的那个，它是一个 cone anisotropy 的 phase， 所以我们觉得是因为你有这个 cone anisotropy， 你 break 了 emergence symmetry， 所以它给你才可能有这种 topological。对，谢谢。
感谢您的报告。是想问一下这个，就是在anomalous conductivity 里边这个。sigma xx to 1.6， 为什么它只有在高温能看到，在低温消失了？
你说 NCO 吗？就是 Skarmian 这个东西，它其实应该在低温是要消失的。
说这个 sigma xx 1.64方这个
哦，
这个
因为
metal 的行为，它不是会 once I thought it should be enhanced when the system become more localized。
不，它在低温下，它实际上是更加 conductive 的，对吧？然后我们发现的是，对，因为它是一个 metal 嘛，所以它的 dirty metal behavior disappear at low temperatures make sense 的。但是我们更重要的是看到它实际上是和我们的那个 weak localization region 是 tag 在一起的，就是说在低温下是你 resistance 有个小的 upturn， 那个就消失了，然后我们就消失。我们是看到消失了，这有可能就还是要问一下做理论，这有可能要么你就是有dimensionality crossover， 你从3D 到2D， 可能你的整个 scattering 的那个。
按照您的理解的话，就是在这个 2D limit， 然后 localization 这个效应出来了之后，它的反常或者应该是什么行为？就还是这个 T independent 的这一项主导。
我看到的是它主导，对，就是说，但是就是说它主导的原因是另外一个被困起掉了，就是你说那个 impurity scattering 那个 1.6 那个 scaling 就整个的就被困起掉了，对。但是我们是看到在低温下，如果你是特别薄的 film， 这一项消失了，是 1.6 的又出现了，就是我给你看一下那个。
如果要是时间会比较长的话，我可以建议我们下午
可以。
转一圈。
对，但我就飞快的秀一下这个数据，飞快啊！好，就是你看到这个很薄的情况下，它已经没有了，这个是还是平的，对吧？这个是因为这个 film 进入了 strong localization 的 region， 就是我们就是 construct 这个 phase diagram， 就是说。你在这个 localization region 才有这个主导的，你在 strong localization 就只有这个 sigma to 1.6 term， 所以的确是
这个直域化的这个强度还有 crossover。
对，就跟 correlation 有关。
你用中文给报告挺好的。
对，但是因为我就是关键词不会。
你可以讲英文啊！你真是那个张老师有什么？
对，我就怕你不是急着走嘛。
对我稍微有点急哈，不要没有关系。
对，我就还有一个简单问题，就是关于您那个看到这种线性磁种嘛，我看您还没有展开说一下是什么原因。
这个我其实问过刘谦老师，刘谦老师说他说这就是因为这是 anti-ferrimagnetic 的，如果你做那个你算它的那个 Barré-Face 的话，它和 anomalous Hall effect 其实是一模一样的。原理。
这个反常化的很多材料，并不是都是这个linear。
对，他是说是 anti-ferrimagnetic material， 因为我这是个 ferrimagnetic， 我有2个 sublattice 是反的。他觉得这个就是因为我有这2个 set， 它的一个有点像 canceling effect 的那个2个 sublattice contribution。他们其实有篇 paper， 他们也很拽的，就是放在 archive 上，从来没有 publish， 但就是 discuss。
他说是因为你处于对 quantum limit， 就是你第一个能能级上面的没占据第一个，对，它那个是正的，这个里是不是负的？这负的没
是个负的，那个是负组，
还不一样。
对，这还是一个词的。
就说这个不同的大家都讨论了这个问题，
对，
不仅仅是刘老师，比方说也讨论了。
他们是不是说的是那个一个 Townsend 的 Tenorite 里边，就是 WTE2 里边看那个超大磁组那个，是吧？
那个是之后了。
哦，那之后。
不是更很早？
很早，它是
那个是很后面，那个时候也是大家也没有太确定就是很多载流子或者什么的。
Tungsten Telluride 又怎么了？
超大磁度 extremely 就不是 closer，extremely large
最早是普林斯顿他们。
对，
就那个 non-saturated 是吧？
对。
我还是 co-author。
我知道。
特别的神奇啊！我跟你们，我真的那篇文章。
你不是接着走吗？
对是。那个对我其实也再次讲啊，我就是 真的是觉得去洪霞老师组里面当学生挺幸福的。
哦，很幸福。
我认识很多就是他组里面的学生啊 ，star 啊，
一直快乐。
就真的是很快乐的一件事情啊，做学术也很有乐趣啊。然后那个大家就基本上都是，而且 University of 这个 Nebraska-Lincoln， 就尽管那个学校规模不是特别的大哈，但是事实上它培养了很多，就我们都很清楚的，就是很熟悉的老师。包括你比方说像咱们系的
音乐伟老师，
哎，对吧？也是个这个杰出代表嘛啊。然后还有这个，我在那边也认识好多人。
就是像张小成老师嘛，化学系的。
对。
哎，是啊。
哎，张小成去哪儿了？
我不知道，我不认识。
你不知道吗？
啊。
哦，他去哪儿了？他去交大了是吧？
我也不知道，但他
回国了。
博士后学生在科大工作。
哦，是这样的啊。
对。
是。所以，而且那个地方生活也非常舒服。
曾纪言的儿子你不知道吗？
谁？
曾纪言。
你好像跟我讲过啊，我记性不好。那个这个，我就是说啊，真的就是大家就是如果打个广告啊，就是互相之间的传一下，如果有学生啊愿意去那边或者做播，申请当研究生或者是博士后都非常好。好，那个再次感谢一下那个洪老师。好，我是真的得。